This is not your grandma's kind of geometry proof. You've done plenty of geometry proofs in your years of maths, but usually you get one diagram, one situation, and they say, prove something about this, okay? This time, I've got an infinite number of diagrams, okay, which is why you can see this is suitable for a proof by induction, okay? So, how are we going to do this? How are we going to approach it? Well, we're going to start off by approaching it the way that we usually do, which is by testing the first allowable value, which is given to us. Right? So I'm going to test for n equals 3. Now, of course, I've been mentioning the fact that occasionally your first allowable value, even though it almost always is, it's not always 1. And there's an obvious reason for this one, a geometrical one. That's why you don't just blindly start off on the first positive integer. Okay? So n equals 3. Now, before I test it, how should I go about testing it? Now, in this case, it'd be fine just to draw a diagram that shows a 3-sided convex polygon and then get the result out from that, right? But I do want some equations that I can work with, even though for the test case it's not that important. Later on when I'm doing some manipulation with the algebra, I'm going to need equations to work with, okay? So let's let the number of diagonals here, right? Let's just give it a name, okay? So let d of n be the number of diagonals. Okay, so I'm going to test for d of 3, right? d of 3. Is it equal to what we expect it to be equal to? Well, it's 3 on 2 times 3 minus 3. That's 1.5 times 0. That's 0. Is that what you expected? It is. And just to be sure, draw yourself a diagram there. And how many diagonals does it have? It doesn't have any. Okay? Now, just, even though we don't need to in this case, just for my own curiosity, because I find that that's a bit of a weird result. Okay? I'm just going to test the next one, just for the sake of it. Okay? If n equals 4, right? How does it work out? If you do d of 4, you get 4 over 2 times 4 minus 3. Okay, 2 times 1, that's 2. Okay, that does check out, right? Look, here's a try hard to not draw a regular anything. That's pretty regular, isn't it? Kind of looks like a kite. Anyway, now you can see how many diagonals are there. There's the 2 you expect. 1, 2. Great. Okay. So, we've tested for our first allowable value. So far, so good. Step 2 is assume. Assume. Now, by the way, I've been watching you working out as you've been doing this, right? Please do not write assume that n equals k. Assume that n equals k. There's a difference here. What you should say is assume true, and you're implying assume the statement. This statement is true for n equals k, right? Because assuming n equals k, well, n can be anything you like, right? So sure, make it k if you want. Eventually, we'll get to some number k, right? That doesn't mean anything. I'm interested in this whole statement, okay? So you can't leave this thing out, okay? You can't just say assume n equals k. It's not enough. What would that mean? It would mean this. d of k is equal to k on 2, k minus 3. I should have also included the condition for k, where it's 3, 4, 5, and so on. Okay? There's my assumption. All right, now what am I required to prove? Here's my prove step, okay? Well, I want the next case over, k plus 1. By the way, here's a good moment for me to mention that, just like your first allowable value is not always 1, right? Your immediate next case is not always k plus 1. And you might have seen one of the questions that I gave you. I can't remember which heading it was under, but the actual values that we're interested here were not one integer, the next integer, the next integer. I think the example I gave you was odd integers. So it was 1, 3, 5, 7, and so on. Okay? In which case, what would the next allowable case be? It would be k plus 2, wouldn't it? And it leaves out the even ones. It has to. And if you try it and you try k plus 1, it rapidly breaks down. Okay, so be careful. Little traps to fall into. What's it look like? k plus 1 on 2, and this will become k minus 2. Yeah? Okay. Now, everything so far has been on autopilot because you do this, you tick the boxes, you get to here. But now what? Where do you even begin? Okay. Do you start by writing this assumption down and then try and work with it in order to, like we did with inequalities yesterday? Or do you start with one of these sides and then try and do some algebra stuff to it to put in your assumption? Let me stare at it with me for a second. What kinds of alternatives do we have here? Does anyone have any suggestions what we might do? What might be a valuable starting point for us? You remember I said yesterday that for each different variety of proof, right? And this is a geometry proof, okay? This proof step here is slightly different, right? You do slightly different things because what you're trying to prove is slightly different, okay? They're interested in different properties, truths, etc. Being that this is geometry, I could ask this in two ways. I was going to ask, what's your first instinct with a geometry proof? But what I think I might ask instead is, what should your first instinct be, even if it's not right now? What do I always bang on about when we look at geometry proofs? Draw a diagram. That's not a bad idea. Now, there's a problem, of course, with drawing a diagram because, as I said, what does this thing look like? I don't know how many sides it has. Well, when we have a series, right? You've been looking at things like this. Plus 2 plus 3. If I said, I want this series to go on for a long time, but I don't know how long, right? I want n terms. You know what the last term will be, right? But you don't know how many numbers are in between, so what do? You put dots, don't you? You say, there's some number of terms. Who knows, okay? I'm going to do exactly the same thing here. I have a polygon. I know it's convex, that's important, by the way, because if it was concave, it had sides that went in instead of outwards, then the diagonals would change, right? I know what convex polygons look like. Let's start one off, okay? Let's let a polygon be defined by... Now, we usually name polygons like, A, B, C, right? Or A, B, C, D. So our convention at the moment is we use capital letters and we go in series, okay? This might not be such a good idea here because, well, what if there are more than 26 sides, which is possible, right? So instead, I'm going to call them, these are all points, right? Okay, so I'm going to call them P1 for the first point, P2 for the next point, P3. Now, at this point, you get 3 points, you've got a pattern, you say dot, 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 I don't know how far I go. Now, hold on a second. How many points will there be? How many points will there be? Not that complicated a question. The last point will be P of what? This is n-sided, right? 3 sides. I have 1, 2, 3 points. Right? 4-sided figure. 1, 2, 3, 4. Now here, I have a k plus 1-sided thing. Okay, so I'm going to have pk there, and then the very last one will be pk plus 1. So far, so good. Now, how do you draw it? Well, place a point down. Okay. Unfortunately, I cannot draw this accurately. Well, actually, I don't know what any of the angles are really going to be. I'm just going to draw off some interval to get to my next point. Okay, and then I'll draw off another interval to get to the next point. Okay, but then I have dots. Right? So I'll go dot, 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 maybe a few more dots. Let's make it reasonably sized. And then after some number of dots, I will have the kth point. Okay? The next one, of course, is the k plus 1th point. Now what happens? This is the last point, isn't it? Right? Now, when I come to the last point, usually, this last point or this last point, in order to make it a polygon, I've got to close the shape, right? So this guy comes right back over here. Is that okay? See what I've got? Okay, good. Now there's my shape. I want to start doing some work with this, right? But don't forget, this is an induction proof, right? So in order to prove this, I'm going to use this somehow. The question is, where is the assumption? Where is it hiding in what I've got here? Okay? And the answer is, well, it's here, isn't it? I can draw it. Maybe I'll stick with this guy. There it is. There is a polygon with k points, k sides, okay? So I'm assuming something about the number of diagonals that are over here, okay? Now before I go any further, don't put this down on your proof, but maybe you do want to draw it on the side so you can understand what's going on. This is difficult to work with conceptually because it's abstract, right? We can't picture it, you got dots in there, okay? So to make things easier for yourself and understand what's going on, take a concrete example first. This is a classic problem-solving technique, okay? So let's think of one you know about, like say a pentagon. Here's a pentagon, okay? How many diagonals does it have? Come on, you have a formula. Come on, it's got 5 sides. 5 on 2, 5 minus 3. It's 5, isn't it? 5. And let's just make sure we can count them, okay? I count 1, 2, 3, 4, 5. Good, okay? Now, just take that, 5, take that as our k, right? Now, what difference would it make if I went to k plus 1, okay? Well, you add another side. To add another side, you add another point, yes? Okay, so let me, which color should I decide? Let's add another point over here, okay? There's my 6th point, my k plus 1th point, okay? So now, if I extend the polygon over here, that new shape is a hexagon, yes? Now, how many diagonals will it have? Now, you can view it from this point of view, right? But another way to think about it is, this new hexagon, right? It will still have all the old diagonals that I drew in green, won't it? All of those guys are still legitimate diagonals of this new figure. I just have those diagonals plus a few extra ones, right? Where are the extra ones? They're all reaching from my existing points over to the new point I just introduced. Or if you want to think about it the other way, from this point to all of the possible diagonals I could form. Okay, I can't form diagonals everywhere. I can't form diagonals with adjacent points, right? How many can I form? It looks to me like I can form 1, 2, 3. Whoop, I missed. You get the idea. Okay, do you see that? I missed one?
The blue one that you drew. Well, like
yeah, okay, all right. So this guy here, right, which was a side before, wasn't it? Okay. So I have extra diagonals. Extra diagonals? All the previous diagonals, the green ones, right? And new ones in red. Whoops, daisy. 5 plus 4. You content with that? Okay, now how can I bring this over here, right? I can say that this shape in here, right, and I actually have a name for it, don't I? If this is ABC and this is ABCD, what's this polygon called? It's called P1, P2, P3, PK, right? How many diagonals does it have? It has, well, by assumption, it has that many diagonals, right? K on 2, K minus 3 diagonals. Okay? By assumption. So, tick. It's a proof by induction now, because I used an assumption. Okay? Now, how do I get from that shape to the next one? Well, I'll do the same thing I did here, right? I have to add on a new series of diagonals, don't I? Okay? So this new shape, P1, P2, P3, and so on, PK, and I have to include the last point, right? Has that many, whoops, plus. Now, how many new diagonals have I got? Where does this 4 come from? Where does this 4 come from? Well, I can reach all of these points that are across from here, right? And then I get one bonus new one, okay? How many will there be? If you want to think about it this way, right? From this point, there are 2 points that I cannot form a diagonal with. 2 points I cannot form a diagonal with, right? I suppose you could say there's 3 because I can't form a diagonal with myself, right? So that's why I get 3 here, but I'll always get 1 more, which is not from this point, right? So it's 4. Surely, this is n minus 2, right? 6 sides, right? 1, 2, 3, 4. If I made a 7th side, is it going to work? Let's try it, shall we? What would happen? Okay, let me do it dotted, see what we can do. I can do 1 new one here, 2 new ones here, 3, 4, 5. It's still n minus 2, isn't it? Okay. So here, I'll have all the original diagonals, and then new diagonals. Is that all right? See what I've done? If you like, you can illustrate it on this guy as well. You've got this, and that old side, which is now a diagonal. Okay? So what's that equal to? That's equal to, I've got what have I got here? Let's put this on a common denominator, shall we? That's k minus 3 plus 2k minus 2, all on 2. Is that all right? I'm going to keep the 2 around because I know I'm going to need one in the end, so there's no point getting rid of it. Okay. What do we got? K squared minus 3k plus 2k minus 2. 4, sorry, thank you. All on 2. K squared still there. Minus k minus, wait, sorry, have I missed something? Yeah. Yes. This is minus 1, isn't it? Is that better? Yeah, that's better. Because I do need a 2 here. That's how I'm going to factorize. 2. That's why I wrote down 2 in the first place. 2 on 2. And this, of course, you can factorize, can't you? Right? That's your k plus 1, k minus 2, which is exactly what you're expecting. That's this. So it works. Okay. So what was different? This is not like the inequality proof where you start off with your assumption. Okay? I actually think it's very much like the ones you started with, where you work with this, but you need a picture, don't you? It is harder to work with in abstract, so you do concrete ones, and then you can see the pattern, right? And then you can form the algebra and stick the assumption in. Does that make sense?